Hey everyone, welcome to our channel. Before we dive in, please hit that like button and subscribe to help this video reach more viewers. It really makes a difference. Don't forget to click the bell icon so you never miss an update. And now let's begin our story about the amazing universe. The solar system is a very ancient place. It is 4,600,000,000 years old. But at the same time, the solar system is much younger than the universe, which is 13,800,000,000 years old. The Milky Way, our galaxy, is about 600 million years younger, meaning it is almost as ancient as the universe itself. Our galaxy formed when small dwarf galaxies merged together, creating the grand spiral we know. But it turns out that the solar system was born when the Milky Way was already more than 9 billion years old. So what was here, in the place of our system before that? There are several versions, but whatever the case, the appearance of our star itself was the result of a long chain of events, periods of long leisurely development, and several cosmic catastrophes. It is known that the very first stars in the young universe consisted of only 3 chemical elements: hydrogen in greater quantities, a little less helium, and just a tiny bit of lithium. Subsequent generations of stars gradually changed the composition of the universe. Thermonuclear nuclear reactions in their cores created the entire series of elements, and the largest of them, exploding as supernovae, heavier nuclei, including uranium. Each new generation of stars is distinguished by ever greater metallicity, and the Sun is no exception here. Its composition unambiguously indicates that the star formed from material that had undergone nuclear processing in the cores of other stars. Both stars and we, humans, are formed from the same elements, atoms created by nuclear fusion. Containing neutral atoms, such interstellar material is distributed unevenly throughout the universe, forming comparatively dense clouds in places. Unlike most clouds with ionized gas, such clouds are capable of star formation due to low temperature. In the Milky Way, such molecular clouds make up only 1/100th of the total volume of interstellar space. According to scientists' assumptions, from the very beginning, our nebula somewhat resembled the Eagle Nebula. After millions of years, it became more like the Pleiades, where bright stars surround a hazy nebula. The gravitational forces of the Milky Way tore apart the members of our solar nursery into structures like the Hyades. In the end, gravitational interactions tore apart this cluster as well. Molecular clouds do not live long, hardly more than a dozen million years. But here, mysteries of cosmic scales occur. Powerful, fast streams of matter mix, swirl, and gather ever denser under the action of gravity, becoming opaque to thermal radiation and heating up. If the mass of the stellar cradle of the giant molecular cloud was hundreds of thousands of masses of the future Sun, then the condensed, cold, and dense proto-solar nebula in it was only a few times heavier than it. There are different hypotheses about what caused its collapse. One of the most authoritative versions is indicated by the study of modern meteorites, whose material formed back in the early solar system, and more than 4 billion years later ended up in the hands of earthly scientists. In the composition of meteorites, magnesium-26, a decay product of aluminum-26, and nickel-60, the result of transformations of iron nuclei-60, were found. Such radioactive isotopes are formed only in supernova explosions. Such a star that died not far from the protosolar cloud could become the progenitor of our system. This mechanism can be called classical. The shock wave shakes the entire molecular cloud, compressing it and causing it to divide into fragments. Analysis of meteorite isotopes showed the presence of elements with different numbers of neutrons in their atoms. Heavy elements, such as gold, platinum, and plutonium, are formed when neutrons bombard atoms. During such collisions, a neutral neutron can emit a negatively charged electron, becoming a positively charged proton and changing the atom. This process, known as rapid neutron capture, occurs only during the most powerful explosions, which besides supernovae include mergers of neutron stars. And some scientists believe that it was this, and not a supernova, that became the parent of the solar system. The merger of 2 neutron stars could have occurred thousands of light years away from us. That's so close that if this event happened now, it would eclipse our entire night sky. Previous studies have shown that a supernova occurs in the Milky Way galaxy once every 50 years. New observations from the LIGO Observatory have revealed that neutron-star mergers occur much less frequently, about once every 100,000 years. The amount of heavy elements in the solar system suggests that they formed as a result of the merger of neutron stars, not a supernova. However, more than 4.5 billion years have passed since that momentous event. That's a very solid time even by universe standards. The solar system has made dozens of revolutions around the center of the galaxy. Stars swirled, were born and died. Molecular clouds appeared and were born. And just as there is no way to find out the shape that an ordinary cloud in the sky had just an hour ago, we cannot say what the Milky Way was like then, and where exactly in its expanses the remains of the star that became the progenitor of the solar system are lost. But we can more or less confidently say that at birth, the Sun had thousands of relatives. In general, stars in the galaxy, especially young ones, almost always form part of associations linked by close age and joint group motion. From binary systems to numerous bright clusters in the cradles of molecular clouds, they are born in collectives, like in serial production, and even after flying far apart, they retain traces of common origin. Spectral analysis of a star allows us to determine its exact composition, a unique fingerprint, that is, a birth certificate. Here's star HD 162826. Today it is in the constellation Hercules, about 110 light-years from us. Judging by the spectral data, by the amount of relatively rare nuclei like yttrium or barium, star HD 162826 formed in the same stellar cradle as the Sun and belonged to the same cluster. The Sun's family once included from 1,000 to 10,000 young stars that formed from a single gas cloud and were united in an open cluster with a total mass of about 3,000 solar masses. Their union did not last long, and the group disintegrated at most 500 million years after formation. So surely there are other sisters of the Sun. They are scattered even further and lost in the rotating arms of the Milky Way. And therefore the Sun itself was thrown away from the place where it was born. We can never say exactly and confidently what was here before the solar system. The evidence for this was lost in space long ago. But we can observe other places in the Milky Way that give us a rough idea of what it might have looked like at different stages of development. But the most interesting thing is, what could that nebula in which our star appeared be called? Your options. Write in the comments. Also, don't forget to like this video and click the bell so you don't miss anything on our channel. Until new interesting meetings. Throughout its multi-billion-year history, Earth has undergone many changes. On this path, it had different unique stages and turbulent turns. Particularly dramatic episodes apparently occurred 700 to 600 million years ago, when ice covered the entire planet completely, from poles to equator, at least twice. One glaciation, the Marinoan, ended 635 million years ago, closer to the end of the Proterozoic eon. Another, the Sturtian, formed about 710 million years ago. Today, their consequences are found on almost every continent. These incredible periods in the history of our planet gave rise to the hypothesis called Snowball Earth or Snowball Earth. Reconstructing the events of those distant years can help today explain the emergence of complex life that followed them, for it was they that paved the way for the subsequent Cambrian explosion period. When complex multicellular organisms began to diversify and spread across the planet, the term Snowball Earth was introduced in 1989. It combined ideas that geologists, climatologists, and planetary chemists had pondered for decades. At first, many of their colleagues were skeptical about this hypothesis. It was common to think that all these cataclysms were unlikely to have actually occurred. With a growing number of evidences in support of the hypothesis and new data helping to determine the timing of events, more and more scientists embrace this idea, and today the majority of the scientific community trusts it. This photograph captures traces of ancient glacial activity in rocks with limestone inclusions in Namibia. It is known that this rock tends to form in the warmest parts of the ocean. This sandwich pattern is just one confirmation of the idea that glaciers covered the entire Earth, both its cold and warm parts. But what did the planet look like during the Snowball Earth times? This whimsical name describes the appearance of the planet from space, a shiny white ball. Imagine a world where there is no liquid water on the surface at all, only a thick layer of solid ice in all directions. This icy surface is mainly covered with frost and tiny ice crystals that have settled from the cold, dry air, whose temperature everywhere is significantly below zero. The average global temperature dropped to minus 50 degrees Celsius. The water cycle, in which water moves between the atmosphere, land, and oceans, completely stopped. In low latitudes, hurricane winds blow. Under the floating shelf glacier, the dark and salty ocean is constantly churned by tides and turbulent eddies created by geothermal heat slowly penetrating from the ocean floor. That's how our planet looked during this period. This is definitely not a place where life forms would want to develop. But what could have triggered these events? This question is perhaps the most interesting, but the most complex. What was the general condition that made the climate colder and therefore made Earth more susceptible to this phenomenon of uncontrolled ice growth? What then served as the immediate trigger? The snowball events occurred. The supercontinent Rodinia was in the process of breaking up, which lasted about 200 million years. This supercontinent, like any other, contained all or almost all of the planet's continental crust. There is definitely a connection between this breakup and the glaciation. It lies in the fact that the breakup of the supercontinent leads to an increase in precipitation in continental areas, and this enhances the weathering of the Earth's crust rocks. Weathering of rocks consumes carbon dioxide, so there will be less of it in the atmosphere, and therefore the climate will become colder. This breakup entailed another cataclysm, which became yet another immediate trigger for glaciation. When continental land masses break apart, volcanic eruptions occur. In recent years, scientists' attention has been focused on a series of very large volcanic eruptions that occurred in the territory that is now the high Arctic regions of Canada. These eruptions occurred about 717 and 719 million years ago. Volcanic explosions lasted thousands or even millions of years. When fiery fountains of lava form, which emerge over several weeks or months, a strong thermal rise into the atmosphere results. Due to its heating effect, sulfur aerosols can rise into the stratosphere, where they remain for a significant period of time. These sulfur gas particles reflect incoming solar radiation and have a very strong cooling effect. In addition to this, another cause of strong glaciation was the high reflectivity, or albedo, of ice. Ice reflects 55 to 80% of incident sunlight, sending this energy back into space before it can warm the planet. For comparison, ocean water reflects only 12, and land areas reflect from 10 to 40, so these surface conditions absorb more solar heat. An additional factor in cooling the planet is that during the cryogenian period, the sun was 6% weaker than now. The breakup of Rodinia, which entailed prolonged volcanic eruptions and the beginning of the first and longest snowball, coincided in time. This undoubtedly radically changed our planet and then affected the formation of life. There is evidence that bacteria, as well as algae and primitive single-celled organisms, existed during that period. However, gradually the first multicellular animals also emerged. Why? This is a matter of assumptions that are quite difficult to verify today. One idea is that on Snowball Earth, ecosystems could have been more isolated from each other, and this could have been beneficial for the development of new life forms. Greater isolation of different ecosystems could have allowed certain ecosystems to take hold, in which there were more multicellular beings. According to the University of California Museum of Paleontology, when Earth warmed and emerged from deep freeze, a huge explosion of life occurred, known today as the Cambrian explosion. This is the earliest known period in the fossil record when major groups of animals appear over a very short, about 40 million years, geological time period. For a long time, geologists tried to understand what they had managed to discover in Earth's geological record. Just before the first appearance of complex life, there were unmistakable evidences of glaciation even in the warmest regions of the planet. It was very difficult to understand how this was possible. Deposits left behind by glaciers are quite peculiar. They look like cement dumped from a concrete mixer. These ice sheets must have flowed from continents into the ocean. For this reason, today there are many deposits that formed in a marine environment, known as drop stones. pebbles or boulders that fell from melting ice as sediments to the bottom. The biggest problem was that since the conditions were so different from any other period in Earth's history, there was not enough good understanding of the significance of this hypothesis to know whether certain geological data were for or against it. Climate models were needed to see what actually happens under snowball conditions, and this modeling, developed later, was extremely important. The hypothesis itself was long perceived ambiguously in the scientific world. There was a lot of evidence, but there was no good idea about the dates of these events. Among dozens of evidences in favor of the hypothesis, there is the discovery of deep flooding of previously shallow shelves and platforms after ice melting. There are also many paleomagnetic data suggesting multiple inversions of the geomagnetic field, implying glaciation near the paleo-equator for hundreds of thousands and even millions of years. But there are unresolved questions in the snowball hypothesis. For example, dating created a new set of problems. One thing that dating showed was that the two snowball Earth periods occurred in rapid succession and were very unequal in duration. The first lasted 58 million years, and the second only from 5 to 15 million years. Today it is unknown why there is such a big difference in the duration of glaciations and why there was such a short interval between them. For only about 10 million years there was no ice, but then suddenly the planet turned into Snowball Earth again. Over the years, alternative theories have emerged, including the so-called slushball theory, a less extreme version of Snowball Earth. But in the slushball scenario, carbon dioxide begins to accumulate very quickly, in which case the glaciation would be short-lived and the ice would gradually retreat. This is not at all what we see in the geological record. Today it is known that the first snowball lasted 58 million years, which is completely inconsistent with the idea of a slush ball. In addition, snowball glaciations end extremely abruptly, followed by clear evidences of a complete and sharp change in climate to a very hot period. This is also not explained by the slush ball model. Various astronomical hypotheses for the formation of Snowball Earth have also been proposed. In 2005, it was suggested that Earth's glaciation arose when the solar system collided with giant molecular clouds in the spiral arms of our galaxy. However, isotopic verification of their hypothesis has not yet yielded any results. And of course, the key question remains: could something like this happen again in the future? Here, the scientific world is unanimously convinced that it will not happen in the next few tens of thousands of years. This is unlikely because the continents are now too far apart. Today, even in extreme winters, continental ice sheets will form that will stop continental weathering and allow carbon dioxide to accumulate in the atmosphere. And this will all lead to warming, not uncontrolled freezing. However, the future is a very stretchable concept. Therefore, we can only study the history of our planet. Since we live here and depend on this place, it is very important to understand that Earth has not always been as it is today. Snowball Earth, or Snowball Earth, is just an example of the amazing events that Earth has gone through, which we would never even suspect if we did not study geological data, if we did not engage in science. If you like this video, don't be lazy to give it a thumbs up. The more there are, the more pleasant it is for us. Be sure to subscribe to our channel if you are not with us yet. And until new interesting meetings. There was a time on Earth when, surrounded by only a few very small continents, there was one supercontinent. There were no familiar mountain chains or beautiful forest landscapes on it. The land at that distant time was rocky wastelands consisting of lifeless rocks, stones, and sedimentary rocks. There could be no talk of any life here. But in the ocean waters at that time, the picture was completely different. Things were much more interesting there with the animal world. That's how Earth looked about 600 million years ago. This ancient period in the history of our planet is called Ediacaran, or Vendian. For the emergence of life, seawater is more hospitable than the dry soil of land. In the Ediacaran, the oxygen level in the atmosphere was still too low, so the existence of organisms outside of water and in water was impossible. Don't forget to like this video and hit the subscribe button to stay updated with all our content. Make sure to click the bell icon so you never miss a new video. Until our next exciting adventure.